Hi, everybody. Thanks for joining me today. I really appreciate y'all coming out. My name is Trevor, and I'm a student as well as a teaching assistant here at Launch School. And today we're going to be talking all about the internet. Essentially, we're going to be looking at what it is and how it works. And when I got assigned this webinar topic, I was one part nervous and one part excited. And the reason for that is that when I started launch school, like I really wasn't a computer or a tech guy. And while I like knew how to use the internet, obviously, I sort of just looked at it like this black box that I plugged into, and then like emails and like cat videos and stuff like that would just come pouring out of this magic black box. And at one point, like I was in like RB 130 or something like that. So in the curriculum, I was visiting home and I was talking to my family about how I was taking like the software development course and I was thinking about transitioning into a career in software development. And somehow the conversation turned to the topic of how the internet works. And I realized I had no idea, like legitimately none. I could not answer that question. And so if you're in that same place, that's totally okay. Uh, there's a lot more to software development than these sort of like networking topics that we're going to be talking about. And also, this stuff is covered in depth in the LS 170 course. That said, I do think it's a good idea to gain a foundational understanding of this technology that we all use every single day. And so that's really my primary goal with this particular talk. If you're sitting out there in the audience without any real idea of how the internet works, my aim is that in about 60 minutes or so, you're going to have a really solid mental model of how it all works and how all the various pieces of the internet fit together. Okay, so getting into the specifics of this talk, we're going to start off by just defining what the internet is. Then we're going to talk about navigating the web. We're going to explore the concept of like interconnected networks. We're going to talk about the physical infrastructure of the internet. We're going to look at the protocols that govern communication across the internet. And then I'm going to try to tie all those concepts together before having just like a nice Q&A section. Okay. But before we get into all of that, we do have a little bit of housekeeping to deal with. So the first thing that I want to mention is that it's entirely possible that this webinar in particular runs longer than an hour. These things officially don't have a strict duration, and this one is just so jam-packed with information that I wouldn't be shocked if it was closer to about 75 minutes rather than exactly 1 hour. And then secondly, if you need to communicate with me at any point, feel free to do so using the Q&A function on your Zoom toolbar. That is separate from the chat function, but it should be on there. That allows you to ask me a question in real time, which will prompt me to stop what I'm doing and give you an answer. That said, with this talk more than some of the other ones, you might feel inclined to like ask follow-up questions or to have me extrapolate on a particular topic more deeply. And if that's the case, I humbly request that you save that type of question for the Q&A portion at the end of the talk, because it is really easy to get derailed and go down these crazy rabbit holes with this topic. So that said, if I do say something that's just like confusing or doesn't make sense to you and you can't really focus on what's happening until I clear this up, you can use that Q&A function during the talk. It's going to give me a notification. I'm going to stop talking and I'm going to answer your question so that we can move forward. But otherwise, please try to save those questions to the end if you can. And then finally, on a somewhat related note, the recording of this webinar is unlikely to be released anytime soon, if at all. Additionally, I don't have any notes to share with you. So if you feel like you're going to want to review some of the concepts covered in this talk, a super easy approach would just be to snap some screenshots of the more information-dense slides as they come up. I got a ton of slides here, and some of them have a lot of information. So if you want to just grab a screenshot of one of those, you're more than welcome to. Okay. And then my very final note here is that if this is your first webinar here, you should just know that all attendees are muted and have their screens turned off by default. That means I can't hear you, I can't see you, and neither can anybody else. It's just me up here doing my best, assuming there's an audience out there listening. So you don't have to have any anxiety about me hearing you or seeing you or anything like that. So unless you have any questions about any of that stuff, I think we can actually get started. No questions. Awesome. Okay. So what is the internet? That seems like a pretty good place to start the talk, right? And if you type this exact phrase into YouTube, you're going to get about 10 bajillion different videos. Some of them are helpful, some of them are not. And I know this because I watched just about all of them while I was preparing for this talk. But one of the most common types of videos you're going to get, or at least like the most popular type of video, uh, are these things called like man on the street style interviews, where you'll have this person standing on a sidewalk somewhere with a microphone, and they ask random passersby this question. They say, "Hey, what is the internet?" And inevitably, like these things are all played for laughs because nobody has any idea how to answer that question, right? And you get all of these like ridiculous, funny answers, right? Like people will say things like, like, oh, I don't know, it's a cloud, right? Like I plug into a cloud of some variety. That's a word we've all heard associated with the internet. Or, other people might say like, I think the internet is like a satellite or something, and it's in the sky and it like beams down my emails into my computer. And then other people just get super flustered and they go like, I don't know, it's just magic. It's a fairy and it sprinkles pictures of cats on me and stuff like that, right? Uh, Turns out, none of those are quite right, but this does beg sort of an interesting question, which is that we have this technology that each of us use every day. I mean, pretty much all day, every day, if we're really being honest with ourselves. It's completely ubiquitous. And yet almost nobody out there can say what it is, let alone how it works. Like there's a whole nother layer that we don't even get into. And that's sort of an interesting phenomenon. Like, why is that exactly? Why do people not have this preloaded explanation for what the internet is or how it works? And I think it really just comes down to this. Like, basically, the internet is actually pretty complex. And so that fact sort of presented an interesting challenge for me when I went to go create this talk, because I had to come up with a way to manage that complexity. And I had to think about the concessions that I was going to make and how I was going to talk about all this stuff and fit it into about an hour-long talk. And so I just want to be really upfront with you about some of the concessions that I am making. And I want to talk to you about the structure of the talk and kind of how I decided how we're going to be managing this complexity with this really big, intricate, complex topic. Okay, so the first thing that we're going to do is we're just going to formally define the internet. That seems like a good place to start. And so we're going to have a two-sentence working definition that establishes what we're talking about when we use that term, the internet. And then we're going to zoom in and we're going to focus on like one specific use case of the internet, specifically navigating to a web page. Even more specifically, we're going to be talking about what happens when you type www.google.com into your web browser. And that's really important to keep in mind because when you zoom out far enough, all internet communication sort of looks the same. It's just sending data across this vast infrastructure from one device to another. That's essentially what it is. But when you start to zoom in and talk about details and protocols and stuff like that, there can be some really important differences that appear. For instance, the implementation details of sending and receiving an email are actually different from streaming a video or doing a live talk like this one, and that's different from when you just visit a static web page. And so when we're talking about details, please just try to keep in mind, we are talking about the particular use case of navigating to www.google.com. Okay, so the third thing that we're going to do is we're actually going to model that use case based off of our sort of like vague understanding that we all probably currently have. So we'll read the definition, and then we're going to visually represent it in a model. But inevitably, models are just simplified versions of reality, and they just leave parts out. That's what a model is. And so they don't cover everything in depth. And oftentimes, they actually beg more questions than they answer. And so what we're going to do is we're going to repeatedly return to that definition of the internet that we have. And we're going to focus in on and sort of extrapolate on one key component of that definition. And then as we dig deeper into the definition, we're going to refine our model, answer some of those lingering questions that came up. And so essentially, we're going to take like an iterative approach. We're going to look at the definition. We're going to talk about it. We're going to dig into one aspect of it. We're going to come up with a model. And then we start over again until our model gets more and more and more accurate. Okay, so then without further ado, here is our definition of the internet. The internet is a network that allows devices across the globe to share and exchange information. It consists of the physical infrastructure, which makes up that network, as well as the protocols that define how data is exchanged across it. There's a lot there, but we're going to look at this about 10 times throughout the talk, so you will see this definition again. Okay, so now we're going to talk about that particular use case that we talked about, which is navigating to a particular web page. But first, we have to get a few definitions straight here, okay? So the first thing we need to be clear about is that the web is not just another name for the internet. That's a common misunderstanding that a lot of people have, and they tend to use those terms interchangeably, but they're not actually the same thing. So the web can be thought of as a service that can be accessed by using the internet. So broadly speaking, the web is actually a vast information system which can be navigated using these things called URLs, or Uniform Resource Locators. So again, that could be our www.google.com. That's one example of a URL. And so every time you visit a website, you're essentially using the internet to access one particular part on the web, or of the web, rather. And so just to clear this up here, we actually have an analogy that I think is kind of helpful. If you could imagine the online world as a city, okay? The web would be all the buildings that contain businesses and services within that city. So web pages would be like the rooms or the resources inside of all of those buildings. And now the internet would be all the roads, the sewers, and the sidewalks that connect those buildings to one another, as well as all the rules that govern their use. So the internet would be like the streets and the traffic laws, all of the sidewalks and the pedestrian laws or the rules there, and then all of like the sewers and the electrical systems and whatever rules govern those things. I don't really know how any of that stuff works, but I assume there are a lot of rules involved. And then a URL would essentially be an address to a specific building, or maybe more specifically, a room, or maybe even more specifically, like a particular drawer that has a resource in it within one of those rooms, within one of those buildings. Okay, so you can kind of picture how all of those things interact. Great. So that's super abstract, and that's all fine and good. But when I type www.google.com into my browser, what actually happens? And so to answer that question, we have to understand this thing called the request response cycle. And the functionality of the web relies on both clients and servers being connected via the internet, like we already talked about. And so a client can broadly be thought of as a computer with internet access that has the ability to request information or data. And then a server is really just a computer that's always connected to the internet, which can send data in response to those requests. And so, like the term server is super overloaded, and depending on the context you're speaking about, it could mean like a ton of different things. But for our purposes, essentially, you can think of a server as a web server, which is a computer that's basically always connected to the internet, and it's just sitting there waiting for requests to come in. And when it does receive a request, it can serve up the data that's being requested, hence the name. So it serves up a response to that request. Okay, so when you type a URL into your browser, a request for data is sent across the internet and it arrives at some specific server. That server then, hopefully, assuming everything goes right, it sends a response across the internet, which your browser can then interpret as the appropriate web page that you are requesting. Okay, so that actually brings us to our first visual model. It's our first visual representation of the internet. And on one end, you have our client, which is your computer, or, more specifically, maybe your web browser like Google Chrome or Firefox or whatever you use. And then on the other side, you have a server, which is associated with the URL www.google.com. And in between, you have all of these red lines. And for right now, we're just going to say those red lines are the internet. We'll just wave our hands a little bit and say, that's the internet in between the two. And so essentially, you type google.com into your browser. Your request gets sent along the internet to the server. And then your server does all of its server stuff. And it serves up a response. Oops, there we go. Which then gets sent back down across the internet back to you. Hey, not too shabby. That's pretty good. Okay, and that actually brings us to quiz number 1. I did forget to mention that we have pop quizzes. I guess maybe that's what makes them a pop quiz. But I'm going to post up the quiz right now. And it has 3 questions, and we'll just give ourselves about 3 minutes to answer them. If I can find the quizzes. There they are. Okay, it should be on the screen for Uh, I do have one note about the quizzes. I did intentionally select and kind of craft questions that I thought people might get incorrect, because I wanted to use this as an opportunity to clear some things up that I thought, people might get wrong. And so if you don't know the answers here or you get them all wrong, don't be discouraged. It's okay. It just means I crafted really good questions. Okay. Well, we have 80% of people have answered so far, so that means we have a couple people left out there who haven't. We'll give ourselves another, 45 seconds or so. I know I said we give 3 minutes, but maybe we don't need it. We have about 30 seconds left. These are all anonymous too. So if you're worried about answering because you're going to get wrong, nobody's going to know. Go, let's say 5 more seconds. 3, 2, 1. Okay, I'm going to end it and let's kind of talk about it. All right, so question number one was the internet is a service consisting of a vast system of information, true or false? That is actually false. Most people got that right, but not everybody. And so remember, we defined the web as the service consisting of a vast system of information. And the internet is just how you access that. Okay. And number two, servers are devices which are always connected to the internet, essentially waiting around for data requests. That's true. Everybody got that right. And again, in our particular use case, right, if we just zoom in enough, that's all a server is. Okay. And so number three, the exchange of all information across the internet relies on the request response cycle. Most people got this wrong. The key part here is all information. That is not true. Some information is exchanged irrespective of the request response cycle. So you can think about like a push notification that you get on your phone, right? That came over the internet. You didn't request that. It just sort of showed up. And so certainly when you're loading a web page in our particular use case, you need to understand that request response cycle, but just know that not everything that happens on the internet relies on that. Okay. A lot of it, most of it, certainly requesting web pages, but not all of it. Very nicely done, everybody. Okay, good. Moving right along. So again, here's our model on the screen. And honestly, like it's pretty good. It's definitely better than like the cloud model or the satellite or the ferry model that we had at the very beginning, right? But it does leave some questions unanswered. The primary one is that when I look at this model, I ask myself, like, do I really have a direct connection with a Google server like this? Like, if I just look at this model here, it sort of looks like there's just one wire that, or maybe two, that like runs from my computer into a Google computer or a server. And the question is that really how it works? And to answer that question, we actually have to return to our definition of the internet, which again is the internet is a network of networks that allows devices across the globe to share and exchange information. It consists of the physical infrastructure which makes up this network, as well as the protocols that define how data is exchanged across it. So we're going to zoom in on this idea of a network of networks. Well, what exactly does that mean? Well, a network is any collection of two or more computers that are connected in such a way that they can share data between them. So let's talk about that. Two or more computers. So you can imagine here, I have my laptop. That's what I'm doing this talk over, right? And then my phone here is sitting right over there. And if I had the right cable, which I never do, and I always lose it, I could plug them in together And then they could just send data back and forth. Like I could drag photos from one to the other. I could open my text messages on my computer, whatever it is. Well, that's a network. I have two devices, and they are connected in such a way that they can share and exchange data between them. And so, like I said, networks can be as small as two computers in the same room or as large as several billion computers spread across the entire world. Now, most networks actually exist somewhere in between there, so they're made up of somewhere between 2 and a billion devices. For instance, like maybe there's a network, if you work in an office, you might have 50 computers there. Well, it's more than likely those computers are all connected in such a way that they can exchange information without sending it across the internet. That would be what's called a local area network. And you'd be able to share data between all of those computers, okay? But if you think about it, unlike our phone plugged into our computer, we don't just have 50 cables running from your computer in your office to the 50 other computers in your office, or I guess the 49 other computers in your office. That would be chaos. Be tripping all over the place. It'd be horrible. What you actually have are these things called switches and hubs, and they're used to connect devices on the same local area network. And essentially what switches and hubs do is that they have cables that come in and out of them, and they can just direct the information to the right machine where it's supposed to go on that local area network. But now I want you to imagine that you work at the same company, but maybe you have two offices. Maybe you have an office right now in Dallas, Texas, and there's 50 computers there. And then you have some other office up in Beloit, Wisconsin, and there's another 50 computers up there. Well, you don't have switches and hubs and cables that run from Dallas, Texas, all the way up to Beloit, Wisconsin. At least your company didn't put that infrastructure in place, that's for sure. What you have are actually these things called routers. And routers can be used to connect devices on a local area network. That's true. They can do the same sort of stuff that a switch or a hub could. But further, they're able to connect different networks with one another and then direct traffic between them. So again, you don't have cables running all over the place from Dallas to Beloit. What you have are these radio waves being transmitted between routers there. And so you have these two local networks. You have one in Beloit, one in Dallas, and then you use a router to direct traffic between those two different networks. Okay, so we all have some experience with routers because we've all used Wi-Fi. I mean, we're probably using Wi-Fi right now, at least most of us. And so the question is, what network is that connecting you to? It's not sending you up to Beloit, probably. Because remember, that's the point of a router. It connects different networks together. And so the router in your home is used to connect your home's local network to a larger network that's provided by your internet service provider or your ISP. And it does that via this thing called a modem, okay? So your ISP is like Comcast or AT&T or whoever, whatever company that you pay your internet bill to, basically, okay? Okay, and so that actually brings us to our next model here, and wow, this model is way more complex than our first one, or at least it has way more devices on it. So let's take a look at what's going on. So now, instead of just having this straight shot in between your computer and the Google server, what you have are all these other devices, right? Like you have these little things here, these little router guys. We have a little switch or a hub over here. And then, of course, you have your own local network over on your end that connects to your router. We have this big thing that's just sort of indicating this broader network that's provided by your internet service provider. And then this might be like your neighbor's sort of local area network. And then again, on the top side, we actually have servers for YouTube and for Google. Because if you think about it, like not all of the internet is hosted on like one server. YouTube has a bunch of their own servers. Launch School probably doesn't have their own servers. I don't know. They probably rent somebody else's. And then Google is over here with their own servers. And it turns out that Google is actually a pretty big company and they have a ton of data stored. So they don't just have it stored on one server. Of course, they have all these multiple servers that are probably connected by switches and hubs and stuff like that. Okay, so if we follow this along here, it actually functions pretty similar to our first model where we have this request and it gets sent along and it hits a router. And then it jumps to this other network over here and then gets sent up to this router and jumps over to this router. And then it eventually makes its way up to the Google server that it was meant to go to, and then Google does its server stuff and it serves up a response that does the same thing. And it just jumps from router to router, from network to network to get to your home network and then eventually your computer. Okay, so this model actually answered one really big question for us, which was, do I really have a direct connection with a Google server? And the answer to that is not really. Like you don't have a direct connection. It's not one wire. However, you are connected because the network that you're on is connected to the network that the Google server is on. And then data is just directed between those networks via a series of routers. Okay, so that actually brings us to quiz number 2, which I'm about to launch up now. All right, we have 70, we have 80, we have 85% of people have answered. So we got a couple people left out there. We're going to wait another 30 seconds or so if you would like to submit your answer and to have your voice heard and be counted anonymously. Okay, 5 seconds left. Anybody out there who hasn't answered yet? All right, let's take a look. Great. Okay, so number 1, how many devices are needed to form a network? Most people got this correct. At least 2. You need 2 devices because, again, the definition of a network is 2 or more computers that are 2 or more devices, we'll call them, not necessarily a computer, connected in such a way that they can exchange data between them. So 2 or more. Which devices direct internet traffic between different networks, like different local area networks? Routers is the correct answer there. Switches can direct traffic within one network, right? Like in your office building or whatever, maybe you have a switch that directs the traffic. But if you're making a jump from one network to another, you need a router to do that. And then number 3, it is possible to be connected to the internet without being a part of any network at all. True or false? That's actually false. It's a little bit tricky to think about because you could think, well, what if I'm in the woods and I have a cell signal or whatever and I can connect to the internet, but it's just me there. I'm not in an office building. I don't have my laptop. I just have one device. Yes, but that device is connected to the internet. The internet itself is a network of networks. And so you can exchange information with other devices, which means by definition, you are a part of a network. Okay. Nicely done, everybody. Thanks for participating with that. I appreciate it. Okay, so here's a model again. And again, wow, this is really starting to look like a thing that sort of resembles the real internet, right? Like there's a lot going on here. But again, it does sort of beg some additional questions. So first of all, we have all these devices, right? We have some routers, we have a switch or a hub too, and then we have all these different computers and things like that. We defined all that stuff. We already know what those things are. But what exactly is all this red stuff connecting it all together? Like up until this point, we're just calling that red stuff the internet. But like, what are those red lines? Like in real life, what are they and what are they made out of? And then further, we have these requests and responses that are just indicated by a little envelope there. You can see those. Uh, but what are those made out of, right? Like they're not envelopes. What are they? We're talking about real life here. They have to be made out of something. So what are they made out of? Well, to answer that question, we return again to our definition of the internet, which is the internet is a network of networks that allows devices across the globe to share and exchange information. It consists of the physical infrastructure, which makes up this network, as well as the protocols that define how data is exchanged across it. So we're going to zoom in on this idea of our physical infrastructure. And so the big key takeaway of this whole section, we're going to talk about a bunch of stuff, is that every device with access to the internet is physically connected in one way or another. I'll say that again, because it doesn't seem to be true, but it is. Every device with access to the internet is physically connected with one another. Some of these physical connections are things that you can see, like electrical cables or fiber optic cables. You know, they're things that you can see and you can touch. While other connections take the form of radio waves, which we can't see, but they're still undeniably physical. And if you question that fact, here's a little test you can run. Don't do this right now, but after the talk, I want you to go and find your router, whatever you're using to connect to your Wi-Fi, and I want you to take it, and I want you to put it in the closet or something in your bedroom, and I want you to put a bunch of blankets on top of it, and then I want you to go out into your garage or down the street or something like that, and I want you to tell me how good your internet connection is. Well, it's not going to be so good anymore because you physically blocked those physical radio waves. You put blankets on top and the radio waves can't get through, and then you move to a different room and they can't get through the walls anymore. So you might be saying, well, okay, you just listed three different physical things here. I have electrical cables, I have fiber optic cables, and I have radio waves. Why do I need all three of those? Wouldn't one type just be the best? So we just use that one. Well, it turns out that each of those different types or those things carries their own costs and benefits. So let's just kind of talk about those. If we're going to compare electrical cables with fiber optic cables, electrical cables are essentially just like copper, like a copper wire that's wrapped in some kind of non-conductive material. And so they're pretty cheap to make. They're not very expensive. And they're really like durable and robust. Like you can bend them, you can twist them, you can stomp on them. It's not going to break. You got just a copper wire in there, right? Fiber optic cables, however, actually have these really tiny little strands of glass that run through them. And so they're much more expensive to make. And then additionally, they're way more fragile because, again, they have glass inside of them. On the other hand, electrical cables transmit electricity, and then fiber optic cables transmit light. Well, light travels way faster than electricity does. So electrical cables are cheaper and more durable, but the information they transmit doesn't move all that quickly, relatively speaking here. Fiber optic cables are more expensive and more fragile, but they transmit data very, very, very quickly. Now, the other one that we have, of course, are radio transmitters and receivers. And I think the benefit there is pretty obvious. Like, you don't need a physical tether. There's somewhere between 5 and 10 billion devices connected to the internet at any given time. And so you could imagine if all of those things had to be plugged into one another. It would just be absolute chaos. Again, we'd be tripping all over the place. The roads would be covered in wires. You couldn't drive. Like, it would just be a nightmare. And so that's great, but the drawbacks are that you couldn't just rely on radio waves because they can't travel all that far, relatively speaking. For instance, they can't travel across the ocean. And then also, as we talked about, they can be physically blocked by like walls and blankets and stuff like that. So if somebody builds a wall in the wrong place, like it can mess with the internet signal. And so there's cost and benefit to all of these options. And really, we need the combination of all three to make the internet work as well as it does now. Okay, but really the whole point of this big physical connection stuff is that without these physical connections, exchanging data across the internet would be impossible. It couldn't happen. And so this sort of like counterintuitive fact leads some people to say stuff like this. This is the late Senator Ted Stevens from Alaska. He famously said that the internet is a series of tubes. And, like He was pretty heavily ridiculed for this. And if you're like most people, you hear a statement like that and you go like, that's just about the dumbest thing anyone's ever said. But actually, there's a grain of truth there. Like what he said is almost kind of sort of not incorrect. And if you question that fact, I submit to you this image. This is a map of the submarine fiber optic internet cables. So that means that each of these red lines on this map represents a physical cable, kind of looks like a big fat tube that is running from one dot to another on the bottom of the ocean. And that actually makes up a big part of the internet. And so the fact is that you can be over here in like, I don't know, like Miami, we'll call it, like that little dot down there in Florida. And you can send an email to your buddy in, I think Zambia is like maybe down here-ish. And the reason that is thanks to these tubes that are running across the bottom of the ocean. And so that's the sort of thing we're talking about when we're talking about the internet's physical infrastructure. It's honestly kind of mind-boggling. I mean, like if this is your first time seeing this map, your mind might kind of be blown. Like I know that mine was. But after I took a second and I processed this information, I was pretty quickly struck by another question. I'm like, okay, that's a lot of tubes. We got all these fiber optic cables running on the bottom of the ocean, a lot of sharks down there. Do they ever get attacked by a shark? And it turns out that yes, occasionally sharks do bite the internet. And so what you have on your screen here is an actual photograph from an actual submarine security camera video of an actual shark biting an actual internet fiber optic cable. And I included this picture in this talk for two primary reasons. So the first one is that the next time your internet goes out, depending on where you are in the world, I would like you to remember the fact that there is a non-zero chance that the cause of that outage is a shark attack. So that's pretty wild. The second, and really honestly the real reason, is that I just want to drive home that the internet, which sort of seems like this weird abstract thing that we picture as a cloud or a satellite up there somewhere out in the ether, right, actually has this real, tangible, physical element to it that exists in our real physical world. All right. So we have all these wires and cables and radio transmitters all over the place, and they're obviously transmitting something, right? But what? What are they transmitting exactly? Well, as you might expect, they're transmitting electrical impulses, light, and radio waves. And because if you think about it, that's all that can be transmitted across those particular mediums. Okay, so you might be going, well, that's fine and good, I suppose, but I'm not trying to send my friend electrical impulses and flashes of light. Like I am trying to send him an email, or I am trying to send her a song I like, or a funny video. So why do I care if I can send this light impulses and electrical impulses and stuff like that? Well, it's because that allows for the transmission of what's known as binary data. And I think most of us have probably heard the term binary, particularly in relation to computers. But essentially, binary can be thought of as a language consisting of exactly two digits that can be represented by 1 and 0, on and off, true or false. And so as a way to understand how that might work, you can think about English as a language. In written English, we have 26 digits. And with those 26 digits, you could write the Iliad and the Odyssey. You could write a text message to your buddy. You could write like the script for the Twilight movies, like whatever. Okay, you can write a bunch of different stuff. And so you have a lot of things that you can express with just those 26 digits. And binary is sort of similar, only it has 2 digits. And the reason that that's particularly useful when we're talking about computers is that at a really deep level, meaning like the level of the hardware, binary is sort of all that a computer understands. So all the computer code that you write and all the data and the information that you care about, so all the words and the pictures and all the videos, all of that gets translated into binary by your computer. And the reason for this is that inside of your computer, you have a ton of these little things called computer chips. We've all heard of those. And inside of those chips, you have millions and billions of transistors. And these transistors are just these little electrical devices that can either be on or off, 1 or 0, true or false. And so there's all these little switches in there, like billions and billions and billions and billions of them, and they can all be either on or off, binary. So you stack all of those on top of one another, and you can express all of this really complex information. And so the reason that binary data in the form of bits of light, electricity, and radio frequencies is useful at all is that computers are able to take that data and translate it into something meaningful to us, human beings, on either side. Okay, so let's take a look at our third model here. It looks a lot like our second model, only I added like a couple little doodads here, like on the end of the wires, and I also added a legend sort of up in the corner. And essentially, I'm just indicating what the red stuff is. Please just appreciate here, I'm not an electrical engineer. This is not a perfect electrical schematic explaining exactly how the internet works. For instance, like I do have like a fiber optic cable that just turns into an electrical cable. And I don't think that happens in real life, but you get the idea, okay? But essentially, we submit a request, and now we don't just call it a request. We see that it's actually made of binary data. And that starts off as sort of like radio waves. And then it gets turned into electricity somewhere up here. And then it gets turned into light across our fiber optic cable. And then it eventually makes its way to our server. And then our response is just different binary data that gets sent along that same sort of physical medium. All right. So that answers a few of the questions that we had. Primarily, I get that the red lines are the internet, but what are they actually? Well, the red lines are the physical infrastructure of the internet, consisting of electrical cables, fiber optic cables, and radio transmitters and receivers. And then the other question we had is, what are those requests and responses like actually made of? The answer is that they're made of binary data in the form of electrical impulses, light, and radio waves. Okay, so that actually brings us to quiz number 3. Okay, we are going to go another like 45 seconds or so to allow the remaining 25% who have not answered yet to answer. Go. We'll call 5 more seconds. See, anybody going to surprise me by sliding in the last minute here? Somebody did. Well done. All right. All right, let's share these results and let's talk about it. Okay, so number one, which of these transmit data the fastest? Fiber optic cables actually do, because they're transmitting light. Not a lot of things out there move faster than light. So fiber optic cables for speed. They are expensive though, and they tend to be a little bit fragile because they got glass inside of them, but they are fast. Number three, giant Ethernet cables run across the bottom of the ocean. Man, I love that I put this question in here. That's false. That is very tricky. An Ethernet cable is a type of electrical cable. We don't have electrical cables. We have fiber optic cables. So that's really kind of a trick question. Sorry about that. The reason that we wouldn't want to use an electrical cable is because oceans are big, countries are far apart, and so we have to travel very, very far. And so you want to do that quickly. And so therefore you would use a fiber optic cable, not an Ethernet cable to do that. Number three, the information traveling across the physical infrastructure of the internet does so in which language? binary. HTML, I think we touched on HTML at the very, very end here. We might not. That is certainly related to like web pages and stuff like that. But certainly when it's traveling across like a radio wave or something like that, you're just sending some binary. Okay, awesome. Very well done here. Okay, our diagram here is looking pretty complex, and I think that complexity begs a few questions. So the first of which comes from the fact that when you look at this picture, you got radio waves, you got electricity, you got beams of light, and they're all just seemingly like shooting all over the place. Like, how in the world do our requests and responses ever get to where they're supposed to go? It just seems like chaos out there, right? And then furthermore, once it gets there, how does the server even know what to do with it? You just shot it a bunch of radio waves or something. And then when your computer gets that response, like, how does it know what to do with that? Like, of course, they both understand binary, but like, how does that Google server always end up sending me the right thing? It never sends me a different web page. It's always the one I requested. How is it that reliable? And so to answer those questions, we, for the final time, I promise, return to our definition of the internet, which is the internet is a network of networks that allows devices across the globe to share and exchange information. It consists of the physical infrastructure which makes up this network, as well as the protocols that define how data is exchanged across it. And so we're going to zoom into this idea of protocols. And essentially, protocols are just systems of rules which govern the transmission of data across the internet. And there are many different protocols concerned with different aspects of this data transmission. And so that might seem kind of odd because you might be saying, well, if this is all concerned with transmitting data across the internet, why don't we just have one big set of rules that just covers everything? And the answer to that is actually twofold. So first, we have different aspects of data transmission that we need to have different types of protocols for. And then secondly, we have different protocols to address the same aspect of network communication, but in different contexts or with like different use cases. And so to clear that up, we have a hopefully useful analogy here. So if you think about written communication as an example, you can think about the different layers of protocols that we all just sort of take for granted. So for instance, like we all have rules that govern the order of letters in a word when we're writing. We might call those our spelling protocols. We have rules that govern the order of words in a sentence. We might call that like our syntax or our grammar protocols. And then there are also like rules that dictate the order of sentences in the overall message. And so you might maybe call those like our storytelling or like our messaging protocols, right? And then furthermore, we actually have different protocols at each of those sort of layers that you would apply if you're writing a resume versus if you're writing a text message to a friend or something like that. So in those two different contexts, you might have completely different spelling protocols, completely different grammar protocols, completely different storing protocols that you adhere to based on the context. And so if we're trying to understand all of the different internet protocols that are at play here, most people typically rely on a layered model to visually represent it. And just like I was talking about with written communication, where there are essentially different layers or groups of protocol that operate at those different layers, so the different groups of protocols that operate at different layers, like our spelling, our grammar, and our storytelling layers. So we're going to talk about a common model that's known as the Internet Protocol Suite, alternatively known as the ICP IP model. And within this model, there are 4 layers of protocols. And as units of data are passed down through those different layers, different protocols are going to be used to add additional information necessary for our data to make it safely across the internet. And one way to picture this is to imagine the data that you want to send across the internet sort of being passed down between these 4 different layers. And at each layer, the data is sort of processed or encapsulated or sort of wrapped up in additional information that's provided by each protocol. Okay, it's getting a little bit abstract here. So I do have a few words of caution for this last little section that we have. Okay, so the first one is that the Internet Protocol Suite is just a model for how these protocols are applied, right? And models, like we already talked about, are inherently imperfect. They're simplified versions of reality. And so there's this British statistician named George Box. And the only thing that anybody seems to remember about George Box was this great quote that he had where he said, all models are wrong, but some are useful. And the Internet Protocol Suite is one of those. It's a model that's wrong, but useful, right? So furthermore, we're about to look at a simplified version of this Internet Protocol Suite model. So we're not even looking at the full thing here. I kind of sanded off some of the edges. So we're simplifying things even further. So when you start thinking about all the different ways that this might be applied in real life when you're sending stuff across the internet, just know that some of the details get a little bit fuzzy, and I'm just abstracting a lot of that complexity away. And then my final word of caution here is I'm going to throw a whole bunch of acronyms and like foreign terms at you. Like I'm going to be talking about stuff like TCP, IP, TLS, DNS, SMTP, like all that sort of stuff. Don't sweat those details too much. Like, I don't expect you to walk away from this one talk knowing what all of those acronyms mean. I'm just going to use those terms to give you a little bit of exposure to them. But all this stuff is covered in a lot of detail in LS 170. So if you go through the core curriculum, you will end up learning all this stuff. Okay. All right. So let's look at this thing. We have our Internet Protocol Suite, and as promised, it's a model with 4 different layers. And at the top, we have the application layer, and then we have the transport layer, and then we have the internet layer, and then we have the link layer. Okay, so essentially what happens at the application layer is the data that we're dealing with is going to be structured in a way that it can be understood by any receiver on the internet. So if you're requesting a web page, you're going to use one protocol. And then if you're sending an email, you're going to use a different protocol at this layer. Like we talked about, different protocols exist here. They operate at the same layer, and it depends on the context. But all of the protocols operating at this application layer are really dealing with like structuring the data correctly. Okay, so our structured data then gets passed down to the transport layer. And essentially at the transport layer, the data is prepared to be transported across the internet. That makes sense, right? So maybe it gets separated into these little things called packets to make the data more easily manageable. And they can be put together in the correct order on the other side. And so maybe like all of those little packets get encrypted or encoded. So if somebody was to grab one out of the sky and try to read it, they're not going to be able to. Or maybe like all of our data gets provided with information that just makes the transport like a little bit more efficient or reliable. Okay. And again, if you're submitting a form on a web page, like you fill in the form and you hit enter or whatever, you're going to use a different protocol at this transport layer than if you're doing like a video chat like this, for instance. So again, we have a same layer, different protocol, depends on the context. Okay, then your data gets passed down to the internet layer where those data packets are given a source and destination IP address, which essentially just uniquely identifies the specific machines that are going to be sending and receiving that data. And a little sidebar here. So an IP address is a completely unique address given to a device when it joins a network. It looks something like this, some numbers with some dots in there, right? And there are a few structural things that make this really useful for identifying a specific device on the internet. But the primary thing to keep in mind is that an IP address indicates where a device is located on the internet, which means that it changes as that device moves around and joins various different local networks. And I actually think that's a pretty common misconception that people have. I think a lot of us have heard the term IP address, and we sort of assume that our laptop has an IP address. But that's not really true. Like your laptop wasn't given an IP address that it carries around for its whole lifetime. When you join the internet through one network, it gets assigned an IP address. And then if it joins the internet through a different network, it gets assigned a different IP address. So if you're working from home and you're connected to your home Wi-Fi, you'll have one IP address connected to your computer or associated with your computer. But then if you go to a coffee shop across town and you sign on to their Wi-Fi, your computer is actually going to be associated with a completely different IP address. It doesn't stick with your computer. Okay, so in any case, our data packet gets passed down to the link layer where it's provided with information that ensures it's sent to the correct machine on the local network. So before it even gets to the internet, it has to get to like the router or whatever it needs to go to on that local network. And so there's a little bit of processing that needs to happen at that link layer to make sure that happens correctly. Okay, so now we're going to specifically look at our use case of visiting a web page on the internet, and we're going to talk about the specific protocols that are used here. And again, we can do this kind of quickly, and if you miss some of the details, that's totally okay. Okay. So at the application layer, essentially you have this thing called the Hypertext Transfer Protocol, or HTTP. And it's used to create what's called an HTTP request. So up until now, we were just calling it a request, but really the full name is HTTP request. And so essentially what happens at this layer inside your computer is that your request for a web page is given a really specific structure so that the server on the other end knows specifically what you're asking for. And then our request gets passed down to the transport layer where it's broken up into these small pieces called packets, which are then prepared to move across the network. And so you have a couple of different protocols that operate at this level, or at this layer, rather. You have the Transport Layer Security Protocol, or the TLS protocol, and that's used to encrypt the data. So again, if somebody was to find one of our packets, grab it out of the sky or whatever, and they try to read it, they can't. It's encrypted or sort of encoded, right? TLS provides that. And then the Transmission Control Protocol, or TCP, is used to add information that's necessary to ensure our data packets get to the destination in the right order without any orders, like none of them get lost and stuff like that. Okay, all of these packets then get passed down to the internet layer, where the internet protocol is used to add a source and destination IP address, which I think begs the question, how does your web browser know what the destination IP address is? And the answer to that is the domain name system, which you can kind of visualize as like a big database somewhere else that stores all of the associations between URLs like launchschool.com, google.com, whatever, with the IP addresses of the servers that host that web information. So in our example, we type in www.google.com into our browser. Our browser, assuming it's not saved in the browser somewhere, sends a request off to the domain name system, and it says, hey, domain name system, what's the IP address associated with that URL, that google.com? And DNS sends that back, and then we stick that on. And this all happens before that request ever gets sent across the internet. All of that happens at the internet layer, and then our packets get passed down to the link layer, where finally our data packets are prepared to find the correct device on our local network. And here, the Ethernet protocol usually is used to add a source and destination MAC address to each packet. You don't really need to know what a MAC address is, but do know this, unlike the IP address, which gets assigned to your device whenever it joins the network and it changes all the time, your computer does have like a burned in MAC address that never changes. It was given to it when your computer was manufactured. And so that can be used to identify it on a local network pretty well, because local networks, like by definition, are limited in size. And so you can have a hub or a switch or a router that keeps track of all of the MAC addresses of all of the devices on the local network, and it knows where to send things thanks to this Ethernet protocol at the link layer. Okay, that brings us to our fourth model here. We're wrapping up, I promise. And here's what happens. You type in google.com, you hit enter, and here's what happens. So the first thing is that HTTP structures your data into a thing called an HTTP request that happens at the application layer. Then gets passed down to the transport layer, where TCP divides the request into these little pieces and adds information that's needed to reliably deliver it and put it back together once it gets to its destination. Then at the internet layer, the internet protocol adds a source and destination IP address, or IP addresses, so that the data can travel between different networks and knows where it's going. But first, in order to get that, we go, hey, we didn't type in the IP address. We typed in google.com. And so you have to send off this DNS request or this DNS query to the DNS, this kind of database out there. And you say, hey, what is the right IP address of the server I'm looking for? And it says, hey, I got you. And it sends it back, and it gets stuck on there. And that happens at the internet layer. And then finally, at the link layer, the Ethernet protocol adds source and destination MAC addresses so the data ends up at the correct device on the network, on your local area network. Okay, so you got all these little data packets, and they get sent off, right? So now they get converted into binary data, and they go across this physical infrastructure, and they get shot off. And so there's a couple little interesting things here that I want to talk about. The first one is that if you look at the actual binary data here of each packet, it's going to be different, because the data payload is different, and some of that stuff stuck on there by like TCP, for instance, is going to be a little bit different. And so our binary is a little bit different. The other thing I want to point out is that they don't all take the same path. Like if you look, our pink guy sort of takes this direct path where it just kind of shoots over and then goes straight up. But our blue guy kind of comes up here, he shoots over here, goes all the way over here and over here. So why would that be? Well, What's happening is that at each jump between routers, what the router does is it looks at the IP address, the destination IP address, and it makes a determination based off of current network conditions. Is there a lot of congestion? Is there, maybe there's an outage, maybe there was a shark attack and I can't go to this router. I got to go somewhere else. And it looks at that IP address and it determines what is the next best jump for it to make in that exact moment. So at moment one, it might be best to send packet one just in that straight shot, but it just turns out, oh, we have some congestion here or an outage or something. And so packet three takes a totally different path. And that's one of the things that makes the internet really fast, and kind of reliable. Because if you get this one, there's a lot of redundancy there. If you get one little outage, somebody's router doesn't work, and one of the fiber optic cable breaks, there's all these different ways that the router can send it along its path. The other thing to consider is that if they're doing that, they might not actually wind up getting there in the right order. You might not get packet one, packet two, packet three, and then packet four. And so how does our server know what to do with those packets and put them how can it put them in the right order? And that's because TCP, one of the pieces of information that TCP provides, is it might say, oh, this is packet 104, 204, 304, 404. And so if it gets a 104 or a 304, the server just hangs on to that and waits for the 204 and the 404. And what can happen is that sometimes it might get 104, 204, 404. Okay. And it's waiting for three, knows there's supposed to be a three, and it never comes, and it will send a request back to your computer and say, hey, that 304 never got here, and your computer automatically, without you even knowing it happens, can resend that 304 packet, and then the server gets it and puts it back together. And all of that sort of reliability and speed is provided by TCP. It's pretty cool. Okay, we have a question. Jack, I'm going to come back to that. Let me wrap up here, and then we'll come back to that. Okay. Great. Here's our model, or here's our questions, right? So that was a good model. I liked it anyways. Okay. How do the requests and responses know where to go? That was our question that our model was supposed to answer, and it does. It says the packets containing those requests and responses are provided with a destination IP address, which is unique to the intended device on the internet. And then next question, how does the server understand my request? And how does my computer know how to turn the response into something useful when it gets it? Well, the answer is that the requests and responses are structured according to a specific set of rules that all devices on the web understand. Okay, we have quiz number 4. Quick vote. Do you guys just want to wrap up or do you want quiz number 4? First 3 people who answer are going to get it. So tell me in the Q&A. Matt says, let's do it. Let's have it. Daisy says quiz. Great. Okay. We're all having fun. Quiz time. Happy to do the quiz. All right. Let's do the quiz. Just want to be respectful of everybody's time. Quiz number 4. Let's take a look. Okay, we'll go another 30 seconds and let the 25% who have not answered answer if they so choose. Let's take a look. Okay, number one, all internet communication has to adhere to one single set of rules known as the protocol. That's not true. That would be false. Uh, Internet communication in general is sort of governed by or has to adhere to a whole bunch of different sets of rules called protocols, but there's not just one, right? We talked about how one wouldn't do it. Their network communication is too complicated and there's too many different use cases. So we got all these different sets of protocols. Number two, requests and responses are structured being the key word, according to the following protocol. HTTP determines the structure. Remember, that's the one that happens at the application layer. It happens first. And so that's why the thing that we're sending is called an HTTP request. TCP does some stuff and sticks some stuff on the packets. Same with IP. Binary doesn't. But yeah, HTTP is responsible for the structure of that core message. And then number three, routers use the destination MAC address to determine which router to send a packet to next. That would be false. They're actually looking at the IP address. So each router is like, oh, well, this is trying to get to this IP address, so I better send it over here. Okay. Well done, everybody. I appreciate everybody participating and hanging in despite us going over time here. All right. Wow. That's a lot of stuff. You might be sitting out there like, that's all fine and good, my guy. But when I type www.google.com into my browser, dude, just tell me what happens. This is what happens. Okay. So the first thing that happens is that your browser creates an HTTP request, which is going to be structured in a way that other web-enabled devices can understand. Then the request gets divided into packets, and additional data is added to each of those packets in accordance with a set of rules known with sets, not a set, sets of rules known as protocols. This additional data is used to ensure that all the packets arrive at the correct destination in the right order. They include the source and destination IP addresses, as well as information used to ensure safe and efficient travel across the internet. Number three, these data packets are converted into binary data in the form of light, electrical impulses, and radio waves, which are transmitted across this vast physical infrastructure of the internet. Number four, as this binary data travels between networks of connected devices, it encounters routers, which look at that destination IP address and they direct it to the next step along the internet. Then, when these packets arrive at their destination, the server assembles the packets and translate the data that they contain. It structures an HTTP response and then follows a similar process before arriving back to the client, you. Then finally, your computer assembles the packets containing the HTTP response. This response contains the code, which is like HTML, CSS, JavaScript, all that stuff for the web page that you requested, which is then rendered and displayed by your browser. That is what happens. And that is pretty cool. My timing was off there. There you go. All right. All right. So next steps here. Before I open up the floor for questions and address a couple of questions we have, I do just want to say this topic in particular is really pretty dense and it can be pretty overwhelming. But if you found this interesting at all, like if you stuck around to the end, congratulations, I do encourage you to sign up for the core curriculum if you haven't done so already. The LS 170 course in the core curriculum covers all of this in a fair bit more detail than I was able to in about 70 minutes. And then also, just speaking from my personal perspective, this is not Launch School's opinion, this is my opinion. If you found this information interesting at all, I think you're really going to enjoy some of the rest of the curriculum because it can be a little bit more fun and exciting, again, just in my personal opinion. Additionally, if you haven't joined the Slack community, you can make your studying a little bit more fun during the prep courses and core curriculum if you decide to do so. So check that out at launchschool.com/chat. We also have our Launch School GatherTown space, which is this kind of like weird, cool, interactive virtual study space where you can collaborate with other students or just access some kind of like helpful study tools like coder pads and whiteboards and stuff like that. It's pretty cool. It's open to everybody, including prep students. So I encourage you to check that out. You can do that by going to launchschool.com/resources and scrolling down to the Gather heading. And then finally, if you want to know more about this very particular topic, you can, and you just can't wait until you're in LS 170. You can check out the introduction to HTTP, which is available for free to everyone in our open bookcase. So launchschool.com/books. We got a whole book about this stuff. Awesome. Thank you guys so much, very much. I'm opening it up for questions and comments here, but I also have a little form for you to fill out. I'm going to post that link to that in the chat. It's a big, ugly thing. I'm going to make sure that that goes to the right place before I just leave it there. It does. So if you could fill out that form, it'll take you like 2 minutes and it lets me know how I did and what I can do better next time. Okay. Jack says, uh, when TCP is establishing the connection between client and host using the TCP handshake, which we didn't talk about, but that's how you establish a connection between kind of server and client. Do separate data queries/requests need to be made starting from the client transport layer to the server and back to the client transport layer to separate? For separate data requests or for separate packets that contain the raw data for the request. Clue me in on that, Jack, and maybe I can give you a tentative answer. Anonymous says, can you repeat why the HTTP request is divided into packets? I'm sorry, I didn't catch that. So I actually didn't talk about why we would ever want to divide this thing into packets. It's just it's a way to make the internet a little bit faster and more reliable to chunk those things up instead of sending this one huge data request. You imagine something could go wrong, it could get, broken up or whatever it might be. And so sending these multiple little requests or these little packets that sort of can pick the fastest route in real time and then it gets slammed back together is a little bit more efficient. Uh, Daisy says, yeah, okay. Oh, you want the one that just says that. Okay, Daisy. Daisy wants this slide, I think. Aaron says, please present the previous slide, next steps. Oh, cool. I can do that in just 1 second. Isaiah says, when I open an app, does a request go to a server? Yes, it depends. It depends on how the app is structured. We'll keep it within the realm. It gets a little complicated. But we'll keep it within the realm of a web-based application, and in which case, yes. Matt says, I heard one time that if multiple people ask for the same thing and you send it all at once, it would be impossibly slow. I'm not quite sure. Are you answering that question of why we would ever divide this up into packets? Like, what's the benefit of that, Matt? Yeah, regarding the packets. Yeah, it's like it would be slow. It could get corrupted in the middle. It would just be kind of a mess. So it makes basically a lot of the stuff that happens at that transport layer is meant to make the data transport faster and more reliable. And so that's what's going on. Okay, does anybody else have any questions or anything that I didn't? Isaiah said you missed the application part. We'll go back. But essentially what happens at the application layer, we'll go back, is that, there you go, this will work. You can take this. Essentially, you're dealing with the structure of the data, right? So you're sending this thing called an HTTP request. And so you use HTTP, it has to have this particular structure. It's just like text, which then gets turned into binary, but it has to have a heading in the right place. It's got to have all of the actual body of the message needs to be in the right place. And so the application layer is determined, or oh my gosh, concerned with structuring that correctly. Jack says, in order to establish the connection, the TCP handshake has to happen at the transport layer. My question is, when the HTTP packet is passed to the TCP layer, the transport layer, does the TCP handshake happen separately from the HTTP? Like, does the TCP handshake first establish the connection and then continues to send? Jack, this might be, I have the intuition that we're running into one of the limitations of the model that we're dealing with here because we're talking about these like layers and then this happens at this layer and a thing is passed down when in reality that's not exactly what's happening. I think that's the issue that we're running into. Otherwise, I feel uncomfortable with my ability to answer this question really directly. So, yeah. Oh, the feedback form. Geez, I sent it to myself, which I don't know why that's the default option in the Zoom chat, but it is. So there, I sent it to everybody. Thank you, Daisy. The feedback form should be in the chat now if you want to click on that. Isaiah says, is it correct to say routers are playing a game of telephone with your request? I would not say they're playing a game of telephone because my the association I have with like a game of telephone is that there's a natural degradation in quality, right? Like somebody says like, purple elephant, and then you'd say it 20 to 20 different people at the end, they hear smurple smellephant or something, right? That doesn't really happen. You don't actually like lose clarity if it goes through more routers. But what does happen is that they are passing that packet. I would say it's almost more like hot potato. If we got to pick a game, it's like where they're sort of like trying to go over there, or like a relay, maybe a relay race where they're like, what's the best? Who should I pass it to get it to there the fastest? I think it's more like that than a game of telephone where you lose clarity and definition. Does anybody else have any questions? I'll try to answer them, and if I feel like I can't answer them for whatever reason, I'll tell you, like I did with Jack. All right. Well, thanks for coming out, everybody, and sticking around for 18 minutes over. I really appreciate that. Says a lot about your willingness to learn and put the time and the effort in. So I really do appreciate that. Pat yourself on the back. I'm patting you on the back. Everybody, have a good night or a good day or a good afternoon or whatever it is, wherever you are in the world. Uh, and take care. And I hope to see you all again sometime soon. Bye bye.